Hi, I'll go through some examples of mathematical proof for you, okay? Hopefully you've seen my first video, my introduction video. It's a little bit long, so I've kind of done this set of examples in a separate one, okay? But go ahead and look at my introduction, okay, if you've not done so already. So I'm going to prove some simple examples for you, okay? So here's one. Prove that the product of two odd numbers is odd, okay? Now, if you remember my previous video, I looked at the proof of two even numbers, okay? The product of two even numbers is always even, okay? Now, the method of proof of this is fairly similar, okay? This is what's called a direct proof, okay? Or proof by deduction, okay? But I like to call it a direct proof because it can be proved directly. There are other methods of proof which maybe I'll talk about later, okay? So first of all, we're looking at odd numbers, okay? We've got to define mathematically what we mean by an odd number. Quite simply, an odd number is one number that is either one more or one less than an even number, okay? That's how we define an odd number, okay? As an example, okay, 2m is an even number, okay? So 2m plus 1 must be an odd number, okay? As long as m is an integer. Okay, and that's really important. Remember I said when you introduce a new letter, you've got to state what it actually means. Okay, so we've got 2m plus 1 is an odd number, and then I'm going to write where m is an integer. See how these mathematical symbols are just so helpful in something like this, okay? And proofs are normally made up of a lot of mathematical symbols, okay? It doesn't matter whether you're dealing with a positive or a negative integer or zero, don't forget, zero is an integer too, okay? Because it doesn't actually say anything about positive or negative, it just says product of two odd numbers, okay? And then, because we've got two odd numbers, okay, the implication there being is that there are any two odd numbers, not necessarily consecutive odd numbers, certainly not the same odd number, but two completely different odd numbers. For something completely different, you've got to come up with another letter. So 2n plus 1 is another odd number, okay? And we'll just finish writing this down. And because I've defined for you another letter, I've got to write down what I mean by that, where n is also an integer. M and N are my preferred letters to use, okay? Some people use P's and Q's, okay? It's all around about the middle of the alphabet, M, N, P, Q. We don't use O for obvious reasons, I'm hoping, with algebra, okay? Because it looks like 0 in case you didn't work it out, okay? Right, and then we've got to look at what we're trying to do. The product means multiplier, so we'll test this out, okay? Now when I say we'll test this out, it's because we don't really know with 100% certainty that it's going to work yet. Okay, we're just hoping it's going to work. So that's why I say we just test it out. So we do the multiplication of these, and then we'll just expand the brackets. So this is the algebraic work. So that'd be 4mn plus 2m plus 2n plus 1. Now, can you see why this shows we're getting an odd number? Just take a moment to think about it for a while. And let me just make it obvious for you. Okay, I'm going to rewrite it like this. 2 multiplied by 2mn plus m plus n plus 1. Does it make it more obvious now? It's because this bit here is an integer. Okay, let me just highlight it like this. This is an integer. Because we've defined m and n to be integers, therefore obviously an integer, added to another integer. This will be an integer because you multiply integers together, you get another integer. So all of this is an integer. So what it means is you've got 2 times an integer. This must be an even number. Okay, and so the plus 1 makes it an odd number. And so I'm going to write is odd. And I'm going to say since 2mn plus m plus n is even. And there we go, and that's it. Okay, that's the mathematical proof done. Okay. All right. Now, sometimes we need to be able to prove things are not true. All right. Sometimes you're given a statement and you're trying to prove something's true, but sometimes we need to consider the reverse. Sometimes we need to consider, well, what if it's not true? Well, sometimes when we do that, just finding a counterexample is enough. Proving something is true is incredibly difficult because you'll be able to prove it true for all particular values, as I've shown in my examples already. But disproving something, proving something that's not true, you just need to find what's called a counterexample. Sometimes they're very easy. Have a look at this one. So prove that the following is not true. So I've underlined the word not there just for emphasis. The sum of two consecutive prime numbers is always even. So it might be that somebody, okay, has said to you the sum of two prime numbers is always even. Okay. Now they might not necessarily need the word consecutive in there, okay, because if I take the word consecutive out, it's still not true anyway. But somebody might say to you, look, I know all these prime numbers. I'll give you one prime number, 17. I'll give you another prime number, 41. If I add those together, I'll get an even number. Okay? They might say to you, I know all prime numbers. Okay, so they might say the prime number 7 and the prime number 17. Add them together, you get an even number. I always seem to get an even number. Therefore, I hypothesize, I conjecture that whenever you add two prime numbers together, it's always even. Not always the case, okay? Because what you do is say, aha, what about the number 2? The only even prime number, okay? And obviously, when you add the number 2 to any other prime number, it doesn't have to be consecutive. Obviously, the consecutive prime number is 3. But when you add 2 to any other prime number, such as these, you do not get an even number, do you? Okay? You will get an odd number. Right? And so that's enough to be able to disprove the statement. Okay? You just say 2 plus 3 is equal to 5, not even, and then I'm going to say, therefore, not true. And that's all I need to do. That's all I need to do in my working. Okay? It's as simple as that. This one is what's known as a proof by exhaustion, or at least you can do it as a proof by exhaustion. What that means is I've given you a defined number of values you can actually use and substitute in and show that it actually works. All right? So we're asked to prove the sum of two consecutive square numbers. The sum of the two consecutive square numbers between 100 and 200 is odd. Okay? Now, because I've defined it between 100 and 200, you can actually work out all the square numbers between 100 and 200 and check that it actually works. So consecutive means one after the other. The first square number between 100 and 200 is going to be 11 squared, isn't it? 121. Now, don't forget, it does say between, which means you cannot include 100 and 200. That's what the word between means. And you've got to be able to use these words precisely. Okay? So we've got 121, consecutive means one after the other, so 12 squared is 144. So we'll do 121 plus 144, and we'll just work out what that is. That's 365. Yes, you do have to write down the answers. It's not sufficient to say is odd, you actually got to write down what it actually is, so 365. And then the next two consecutive odd numbers. So we've done 11 squared and 12 squared, so now we do 12 squared and 13 squared. Okay? You can't just jump to 13 squared and 14 squared because then you've missed them out. Okay? So it's important that you are getting each pair of values consecutive as you go along. So 11 squared and 12 squared, 12 squared and 13 squared. Let's add these together, shall we? So that's going to be 313. And then the next two consecutive square numbers, is 169, 13 squared plus 14 squared, 196. So what's that going to be? 205, 365. Okay. All of which are odd numbers. All of which are odd. Therefore, underscore that statement is true. Notice in a proof, you've always got to end with some sort of conclusion, okay? You normally say, therefore, true or is true, since, because, and the statement is true, and the reason is the line above, okay? So that's a proof by exhaustion, because we can actually go ahead and substitute all the given numbers. Contrast that with if I pose the same question, but without that bit. Prove the sum of two consecutive square numbers is odd. Can't do that by exhaustion, because you cannot substitute every single value. Okay, the numbers go up to infinity. Okay, so you'd have to actually do it, using what's called a more traditional direct proof. Let's do that. Okay, so let's have a look at what we've got. We're looking at square numbers. what is a square number? Okay, it's an integer value squared. That's what we think of as a square number. It's not a decimal value squared, is it? Or an irrational number squared. It's a integer value squared. So I'm going to say let m squared, okay, be a square number. Remember what I said about introducing letters, where m is itself an integer. Of course, it doesn't matter whether it's positive or negative integer, does it? Because you square a negative value, it becomes positive. Okay, so that bit's fine. Okay, let m squared be a square number. Then what do we have as a expression for the next square number? Okay, the consecutive square number. Okay, well, in my previous example, I was talking about 11 squared and 12 squared, 13 squared and 14 squared, and so on. Right? So if m is one integer, then the next integer is m plus 1, isn't it? Okay. Then m plus 1 is the next integer along, and m plus 1 squared is the next square number. And notice in this proof, unlike some of the previous ones, I don't need to introduce a new letter, do I? That's the nice thing about consecutive. When you have a proof involving consecutive values, you don't need two different letters. There's a hint for you. Okay, you can just choose one letter, and then the consecutive bit is normally found by doing the m plus 1. Okay, and in case you want to ask, yes, you could do m minus 1 and go the other way. Okay, but I'm more of a positive person, just I prefer the m plus 1. Okay, and then what we're going to do is we're going to look at the sum of these numbers. So now I've got the two consecutive square numbers. We're now going to look at the sum of them and see what happens. So we'll do m squared for the first one, and then m plus 1 squared for the second one. And we'll see what that gives us. All working is needed. Don't skip any stages at all. So when you're doing a proof, all lines of working's got to be clear, because basically you've got to be able to take this proof and show it to somebody who's not necessarily a mathematician, okay, but they can actually understand what's going on. Or you can talk them through what you've written and they can understand what's going on. You can't have any gaps, in other words. A proof should be readable so that it makes sense from start to finish and there's no bits missing. Okay. Another good reason why teachers always say show your working, yeah, because it does prepare you for this topic here. Then we'll just simplify that, so it gives us 2m squared plus 2m plus 1. Now, can you see why that shows that this is an odd number? Think about it for a moment. What I'm going to do is I'm going to make it obvious for you, which is what you should do in your proof as well. I'm going to write it like this, 2m squared plus m plus 1. Now can you see why it's obvious? Because the m squared plus m is an integer, isn't it? If m is an integer, then m squared is also an integer. Integer plus integer is an integer. 2 times an integer is how we define an even number. So you've got an even number there, plus 1. Okay? And I'm going to write is odd, since 2m squared plus m is even. If I had more space, I'd probably also include and m squared plus m is an integer as well. Okay, and therefore it's true. Okay, sometimes I put therefore true. Okay, yeah, I'll put it actually therefore true. But the statement is odd actually covers it. Okay. So my next proof is this. Prove that all square numbers, all of them, are either a multiple of 4 or one more than a multiple of 4. Sometimes these questions, they're really thought-provoking, because sometimes you're introduced to things you'd never previously considered. Had you considered that before? That all square numbers are either multiples of 4 or one more than a multiple of 4? If you find that fascinating, then you're probably a true mathematician. Okay? If you're like, so what? Then you're not. Frankly, okay? So if you consider a degree in mathematics and you're not bothered about that statement, then forget it. You'll not be interested. Okay? Yeah. Short, sharp advice, isn't it? Anyway, let's have a look at this, okay? Because I find that fascinating. All right? Let me just give you a couple of examples. So square number 9. Okay? 9 squared, 81. So 9 squared equals 81. And guess what? That is one more than a multiple of 4, isn't it? Okay, let's go for another square number. I don't know what it is, 17? 17 squared. So 17 squared is 289. And 288 is a multiple of 4. You can check it if you want. Okay. Interesting. Okay, so that's one more than a multiple of 4. Let's go for some other square numbers. So let's go for a really easy one. 10 squared, 100. Okay, don't get much simpler than that. That is a multiple of 4, isn't it? Okay, let's go for another square number. Okay, obviously I won't go for 4 squared because that will obviously be a multiple of 4. 2 squared, clearly a multiple of 4, and so on. Yeah. So let's go for something slightly different. Let's go for, I'm trying to avoid numbers without multiples of 4, okay, so clearly, 4, 8, 12, 16 are square then, they're all multiples of 4, aren't they? So that's why I'm going for something slightly different, okay. Let's go for 18 squared, why not? So 18 squared, 324, okay, that is also a multiple of 4. So these examples are enough to show you. And just another bit of advice, okay, maybe more useful advice than my previous one about universities, okay. Sorry if I put anyone off, but it's true. It is true, okay. If you want to do maths at university, you've got to be interested in all things mathematical, okay, all things mathematical. You can't sort of pick and choose, okay. What was I saying? Yeah, if you're not sure what the question's actually asking you, try some examples. Okay, try and find out what actually it means, and I'm hoping by these 4 simple examples I'm showing you what it means. Can you see clearly that the even numbers all come out as being a multiple of 4 and the odd numbers all come out as being one more than a multiple of 4? So what that means is in this proof we've got to break it up into odd numbers and even numbers separately. Okay, now without those examples you may not have thought about doing that. And that's the importance here, or sometimes think of examples. That's what I do, if I'm honest, whenever I'm proving something. I get it into my head exactly what it is I need to be able to do. Something might look simple from the outset, but just think about, you can write them down if you wish, like I've done here, but just think about some numerical examples so you've got it clear in your head exactly what it is you've got to do. And by choosing these numerical values, I've painted the picture for you. You need to consider odd numbers and even numbers separately. Even numbers are always easier, okay? Well, I find them easier anyway. So I'm going to do the even numbers, okay? So let's just consider even square numbers first. And it's fine, because in considering all square numbers, if you look at all the even square numbers, and then all the odd square numbers, that covers all of them, okay? Sometimes in a proof, it's better to do it that way. So let's look at the even square numbers. Now, what do we mean by an even number again? We mean 2m where m is an integer, don't we? Okay. So 2m squared is an even square number where, and don't forget, you've always got to define any letter you introduce, m is an integer. Okay, it doesn't matter whether m is a positive or negative integer. Again, when you square it, it becomes positive, doesn't it? Okay. So looking at prove that all square numbers are either a multiple of 4. Now what we're going to do is prove that this one is a multiple of 4. Okay. So we look at 2m squared, that is, so I'm going to say it's working space here because I've got to do the odd numbers as well. 2m squared is going to be equal to 4m squared. Simple as that, expanding brackets. Okay. And then you can say which is clearly, I sometimes write clearly, because when it's 4 times something it is clearly. Sometimes mathematicians say it's obvious. The less good mathematicians say it's obvious when it's not. You'll learn who those lecturers are, okay, if you get to university and do it. Okay, there'll be a lecturer that will go through this and say, it's obvious. If it's not obvious, then they've not done their job properly. Okay, but in reality, who's actually going to call out the professor and say, I don't think it is obvious? Okay, you can be brave if you want. I never was. So, which is, I'm not going to write obviously or clear, which is I'm just going to write it the way I see it, which is a multiple of 4. So that's that done. And then we look at the odd square numbers, okay? So odd squares, I suppose I should write square numbers, but I'm not, okay? So what's an expression for an odd square number? Well, remember an even number is 2m, 2m plus 1 will give us that odd square number, okay? So 2m plus 1 squared is an odd square number where decision time. Should I use M or should I use a different letter? Okay. Strictly speaking, I can get away with using M because I'm considering them separately. I'm just thinking about whether I should use a different letter or not. Okay, because when I introduce, and I'm going to keep M there. Okay, because I'm still looking at all values of M. Okay, so I'm good. But just notice how, you know, even I'm considering, oh, should I have used a different letter? Okay, M is fine because it's the workings because it's separate to that bit. Okay, but I'm going to write again where M is an integer, more of a reminder really, and then, excuse me, test it out. So 2m squared is equal to 4m squared plus 4m plus 1. That's all workings required for the simple expansion of brackets. And then I'm just going to write it as 4m squared plus m plus 1. Can you see what I'm doing there? I'm making it more obvious that it's a multiple of 4 plus 1. Okay, so one more than a multiple of 4. Okay, making it obvious. And I'm going to write down which is one more than a multiple of 4. And I should really state, since m squared plus m is also an integer. So I'm going to squeeze it down here, since m squared plus m in brackets is an integer. Unfortunately, I've run out of room. My last aim would be therefore proved. Okay, because we've actually proved it. Okay. But I'm hoping you can see how that has worked. Well, I'm hoping that those examples have been useful for you. I'm hoping you're able to follow them. Going through questions yourself is always difficult. Okay, because it's not like, I'm going to use Pythagoras' theorem again. It's not like as soon as you learn Pythagoras' theorem, you do a whole exercise based around right-angled triangles. No, it's not like you've just learned how to differentiate and then you do a whole exercise on differentiating y with respect to x. No. Okay. Proof can be about anything in the mathematical universe. Okay, there I've used the word universe. Okay. Proof can be about anything in the known mathematical universe. Again, that's why it's difficult. Every single question you get could be just completely different. But what I've given you, I'm hoping, is the basic structure and thinking that you need to be able to prove a given result. I'm hoping you found that useful. See you again, and good luck with all those proofs.